Right now, as you're watching this, you might be living infinite different versions of your life. In one universe, you chose a different career. In another, you never clicked on this video. In countless others, you don't exist at all. This isn't science fiction. It's a serious scientific hypothesis that emerged from our most successful theories about reality. The multiverse concept suggests that everything you see, everything you've ever experienced, might be just one thread in an infinite tapestry of parallel universes. Each one operating under its own rules, its own physics, its own version of what's possible. But here's what makes this genuinely strange. We arrived at this idea not through wild speculation, but by following mathematics and physics to their logical conclusions. The journey begins in an unexpected place. Not in a laboratory or an observatory, but in the strangest realm of physics we've ever encountered. The quantum world, where particles exist in multiple states simultaneously, where observation itself changes reality, and where the very act of measuring something forces nature to make a choice. In 1957, a graduate student named Hugh Everett III proposed something radical. He suggested that quantum mechanics doesn't force nature to choose at all. When a particle faces multiple possibilities, every single outcome actually happens. Not in some abstract mathematical sense, but in concrete, physical reality. Your brain probably just asked the obvious question. If every outcome happens, where do all these other results go? Everett's answer shattered conventional thinking. They split off into separate universes. Each possibility becomes real in its own distinct branch of reality. The universe doesn't collapse into one outcome. It multiplies, creating a new version of itself for each quantum possibility. This wasn't mysticism or philosophy. Everett built his idea directly from the mathematics of quantum mechanics, taking the equations seriously without adding extra assumptions about wave function collapse. His doctoral thesis, developed under physicist John Archibald Wheeler at Princeton, laid out what would become known as the many worlds interpretation. The physics community initially rejected it. The dominant Copenhagen interpretation, championed by Niels Bohr, insisted that quantum superpositions collapse into single outcomes when measured. Adding entire universes for every quantum event seemed absurd, extravagant beyond reason. But Everett's mathematics was sound. His interpretation made the same predictions as standard quantum mechanics while eliminating the mysterious collapse process that nobody could explain. The equation describing quantum systems, the Schrödinger equation, is perfectly deterministic. It never shows anything collapsing. Collapse was added by hand to match what we observe. What if we observe single outcomes not because collapse happens, but because we only experience one branch? Fast forward to the 1970s. Physicists developed something called quantum decoherence, and suddenly Everett's idea gained new credibility. Decoherence explained why we don't see quantum superpositions in everyday life. When quantum systems interact with their environment, the different possibilities become isolated from each other. They still exist, but they can't interfere anymore. Each branch becomes effectively independent. This solved one of the major problems with many worlds. Critics had asked why we experience definite outcomes if everything exists in superposition. Decoherence showed how environmental interactions split reality into non-interacting branches, each appearing classical and definite to observers within it. The math worked. The predictions matched experiments. And no additional assumptions were needed beyond quantum mechanics itself. Then technology caught up with theory in ways nobody expected. In December 2024, Google unveiled a quantum computing chip called Willow that solved the problem in under 5 minutes. The same problem would take the world's fastest conventional supercomputer 10 septillion years. That's longer than the age of the universe by a factor so large it defies comprehension. Hartmut Neven, founder of Google's quantum AI team, made a startling claim. The chip's performance, he suggested, provides evidence that quantum computation occurs across parallel universes. The computational power we're tapping into might literally come from performing calculations simultaneously in multiple realities. British physicist David Deutsch had proposed exactly this in the 1980s. He argued that quantum computers don't just process information faster. They harness computational resources from parallel universes. When a quantum bit enters superposition, it's not just in two states at once in some abstract sense. It exists in two different universes, and both versions are computing. Deutsch looked at algorithms like Shor's algorithm, which can factor enormous numbers exponentially faster than any classical approach. Where does that computational power come from? A classical computer trying every possibility would take longer than the universe has existed. But a quantum computer with just a few hundred qubits can solve it quickly. His answer was simple but profound. The computation is distributed across parallel universes. Each universe handles a small piece of the problem, and quantum interference between universes combines the results. Critics immediately pushed back. Alternative explanations exist that don't require parallel universes. You can describe quantum computation using standard quantum mechanics without invoking many worlds. The mathematics works either way. But here's what makes the debate fascinating. Both sides are interpreting the same successful theory. Quantum mechanics makes incredibly accurate predictions. We've tested it to extraordinary precision, and it never fails. The question isn't whether the math works, but what it means. Does a quantum computer access parallel universes, or does it just exploit quantum superposition in a single universe? The distinction sounds academic until you realize what's at stake. If many worlds is correct, every quantum event throughout cosmic history has spawned universes. The number of parallel realities is incomprehensibly vast, growing exponentially with each passing instant. Yet many worlds represents just one pathway to a multiverse. While quantum mechanics suggests reality branches at the smallest scales, cosmology arrived at multiverses through a completely different route. In 1979, physicist Alan Guth was struggling with problems in the Big Bang theory. The universe appeared impossibly uniform. Regions that could never have communicated with each other had identical temperatures, identical properties. How did distant parts of the cosmos coordinate to look so similar? Guth proposed that a fraction of a second after the Big Bang, the universe underwent inflation. Space itself expanded exponentially fast, doubling in size every tiny fraction of a second. This rapid expansion stretched tiny regions to enormous scales, explaining why everything looks so uniform. The theory solved multiple problems elegantly. It explained the universe's flatness, its uniformity, and why we don't see certain exotic particles predicted by physics. NASA's Cosmic Background Explorer satellite confirmed inflation's predictions in 1990, detecting exactly the small temperature variations the theory required. The 2003 Wilkinson Microwave Anisotropy probe refined these measurements further, verifying inflation's predictions to within 1 to 2%. But inflation had unexpected implications. Physicists Paul Steinhardt and Alexander Vilenkin realized something remarkable in 1983. Inflation might not stop everywhere simultaneously. Quantum fluctuations during inflation could cause some regions to inflate faster than others. Those regions would expand so rapidly that even though inflation ends in some places, it continues overall. Picture bubbles forming in boiling water. Each bubble is a region where inflation ends, creating a universe like ours. But the water itself keeps boiling, constantly producing new bubbles. Inflation becomes eternal, never completely stopping in the global structure. Andre Linde developed this into a detailed framework called chaotic inflation. In his model, our universe emerged from a quantum fluctuation in some pre-existing space. That same process continues elsewhere, spawning universes continuously. There was always a yesterday, and there will always be a tomorrow. The multiverse becomes infinite, with our observable universe occupying an infinitesimally small fraction of the whole. Each bubble universe could have different properties. The laws of physics, the fundamental constants, even the number of dimensions might vary. Some universes might lack stars or atoms. Others might have entirely different forms of matter. This wasn't speculation added to inflation. It emerged naturally from taking the theory seriously. If inflation happened at all, the Lenkins showed, it almost certainly produced a multiverse. The same quantum fluctuations that drive inflation also ensure it continues eternally in some regions. String theory opened yet another door to multiverses. This framework attempts to describe all forces and particles as vibrations of tiny strings. To work mathematically, string theory requires extra spatial dimensions beyond the three we experience. These extra dimensions must be curled up into complex shapes called Calabi-Yau manifolds. But here's the problem. String theory allows an enormous number of possible configurations for these hidden dimensions. Each configuration produces different physics in the three dimensions we observe. The number of possibilities is staggering, with estimates suggesting at least 10 to the power of 272,000 different vacuum states. Leonard Susskind called this vast collection the string theory landscape. In his 2005 book, he proposed something bold. What if all these possibilities are real? What if eternal inflation populates the landscape, with different bubble universes realizing different configurations? This would solve two problems simultaneously. String theory wouldn't need to uniquely predict our universe's properties because different regions would have different physics. And it would explain why our universe appears fine-tuned for life. That fine-tuning is remarkable. The cosmological constant, which drives the universe's accelerating expansion, has a value around 3 × 10⁻122. If it were even slightly larger, galaxies would never form. Slightly smaller, and the universe would have collapsed before stars could ignite. Dozens of fundamental constants show similar precision. The strength of gravity, the mass of electrons, the fine structure constant. Alter any of them minutely, and complex structures become impossible. No stars, no chemistry, no life. Some physicists see design. Others see a puzzle demanding explanation through fundamental physics. Susskind offered a third option. With infinite universes exploring every possible value for these constants, some inevitably land in the narrow range permitting complexity. We exist in one of those rare universes not because it was designed or because physics demands it, but because we couldn't exist anywhere else. This reasoning, called the anthropic principle, remains deeply controversial. Critics argue it abandons the goal of understanding why constants have their specific values. Supporters counter that if the multiverse exists, anthropic reasoning becomes not just valid but necessary. The question becomes unavoidable. Can we ever know if any of this is real? Testing the multiverse presents a fundamental challenge. If other universes exist beyond our cosmic horizon, causally disconnected from ours, how could we ever detect them? This question strikes at the heart of what makes a theory scientific. Traditional science demands testability. You propose a hypothesis, design experiments, gather data, and check if reality matches predictions. But multiverse theories seem to violate this basic principle. You can't visit other universes. You can't measure them. You can't even exchange light signals with them. Critics pounce on this weakness. George Ellis, a prominent cosmologist, wrote in 2011 that the multiverse isn't a traditional scientific theory. He acknowledged that these other universes supposedly exist far beyond any cosmological horizon we could ever reach. The evidence, if it exists, remains permanently out of reach. To Ellis and others, this crosses a line. Science becomes indistinguishable from philosophy or even theology when it invokes infinite unseen realms to explain what we observe in the one realm we can actually study. The comparison to religion cuts deep. Invoking countless invisible universes to explain our universe's properties sounds suspiciously like invoking an invisible creator. Both require faith in something fundamentally unobservable. Both offer explanations that can't be falsified. The multiverse might wear scientific language, but does it truly operate by scientific rules? Yet defenders of multiverse theories push back hard. They argue that physics has already embraced unobservable entities. Before quarks were indirectly detected, they remained theoretical constructs. We still can't observe them directly. Regions of our own universe beyond our cosmic horizon will never be visible to us, yet cosmologists routinely discuss them. The interior of black holes lies forever beyond observation, but physicists confidently make predictions about what happens there. Why should other universes face stricter standards? More importantly, some multiverse theories emerge as unavoidable consequences of well-tested frameworks. The many worlds interpretation doesn't add new assumptions to quantum mechanics. It removes one, the mysterious collapse of the wave function. Eternal inflation follows naturally from inflation theory, which has passed numerous observational tests. String theory's landscape arises from the mathematical structure of the theory itself. These aren't arbitrary additions. They're implications of taking established theories seriously. The testability question becomes more subtle when examined closely. Direct observation isn't the only form of evidence. Indirect testing remains possible through several approaches. If inflation produced a multiverse, that process should leave signatures in the cosmic microwave background. The pattern of temperature fluctuations, the spectrum of gravitational waves, the distribution of matter on large scales. These observable features constrain what happened during inflation and therefore what types of universes the inflationary multiverse might contain. Consider the string landscape more carefully. While we can't visit other universes with different vacuum states, we can test whether string theory correctly describes our universe. If string theory fails observational tests here, its landscape becomes irrelevant. If it succeeds, the landscape comes as part of the package. You don't get to cherry-pick which predictions to accept. The theory makes a bundle of claims, and the whole bundle stands or falls together. Quantum computing offers an unexpected testing ground. David Deutsch argued in the 1980s that quantum computers could only achieve their extraordinary efficiency by performing calculations across multiple parallel universes. When Google's Willow chip recently solved the problem in under 5 minutes that would take classical computers billions of years, Hartmut Neven suggested this performance supports the many worlds interpretation. The task, called random circuit sampling, demonstrated quantum supremacy. Where did the computational resources come from? Critics counter that quantum mechanics works perfectly well without many worlds. The standard Copenhagen interpretation, or newer approaches like quantum Bayesianism, explain the same phenomena without multiplying universes. True enough. But here's what matters. The many worlds interpretation makes the same predictions as other interpretations for any experiment we can actually perform. It's not more testable, but it's not less testable either. The choice between interpretations comes down to philosophical preferences about what's really happening beneath the mathematical formalism. The anthropic principle introduces a different testing strategy. If our universe's constants must fall within narrow ranges for life to exist, and if a multiverse explores all possible values, we should find ourselves in a typical life-permitting universe. Not the most finely tuned. Not the least. Somewhere in the middle of the habitable range. We can test this prediction by measuring constants more precisely and checking if they cluster near the center or edge of life-permitting values. The cosmological constant provides a concrete example. Its observed value sits uncomfortably close to the maximum that still allows galaxy formation. Any larger, and cosmic expansion would prevent gravitational collapse of matter into structures. This proximity to the boundary troubles some physicists. It seems too convenient, like the universe was dialed to just barely permit our existence. Multiverse proponents argue this makes sense if we're sampling from a vast distribution. Life appears where conditions permit it, even if those conditions sit near the edge. Statistical predictions become possible in multiverse frameworks. Steven Weinberg, before the cosmological constant's discovery, used anthropic reasoning to predict it should be small but non-zero. His prediction proved remarkably accurate when observations confirmed a tiny positive value in 1998. This counts as a successful prediction from multiverse reasoning. Not proof, but evidence that the framework can generate testable forecasts. Bubble collisions and eternal inflation offer another potential signature. If our bubble universe collided with another bubble in the distant past, that collision might leave an imprint in the cosmic microwave background. A circular pattern of temperature variations, breaking the otherwise random distribution. Several research groups have searched for such patterns. None found yet, but the possibility remains open. One collision, one clear detection, would transform multiverse theory from speculation to established fact. The holographic principle suggests a more radical testing approach. This idea, emerging from black hole physics and string theory, proposes that our three-dimensional universe might be encoded on a two-dimensional boundary, like a hologram. If true, certain correlations in the cosmic microwave background should appear, signatures of the holographic encoding. Finding them wouldn't directly prove other universes exist, but it would validate the theoretical framework from which some multiverse proposals emerge. Occam's razor complicates the debate further. This principle states that simpler explanations should be preferred over complex ones. Multiverse critics claim that invoking infinite universes violates simplicity. One universe is simpler than countless universes. But multiverse defenders flip the argument. Which is simpler, a theory that requires fine-tuning dozens of constants to precise values with no explanation, or a theory that generates all possible values naturally? The multiverse might be ontologically complex, containing many universes, but it's theoretically simple, requiring fewer arbitrary assumptions. Max Tegmark pushed this reasoning to its limit with his Level 4 multiverse. He proposed that all mathematically consistent structures exist physically. Every possible set of equations, every coherent mathematical framework, corresponds to an actual universe somewhere. This sounds extravagant, but Tegmark argued it's the ultimate application of Occam's razor. Instead of asking why our particular mathematical structure is real while others aren't, you simply accept that all of them are. One simple rule: mathematical existence equals physical existence. Few physicists embrace Tegmark's radical democracy of mathematics. It ventures far beyond current evidence or theoretical necessity. But it illustrates how different thinkers weigh simplicity differently. Is one universe with mysteriously fine-tuned constants simpler than infinite universes with varying constants? The answer depends on what you're measuring. The scientific method itself may need refinement for cosmology's unique challenges. We only have one observable universe. Sample size of 1. Traditional science relies on repeatable experiments and multiple observations. But you can't rerun the Big Bang or observe the universe from outside. Cosmology has always operated under special constraints, developing methods to extract information from a single, unrepeatable event. The multiverse question simply extends this challenge. Perhaps the real issue isn't whether multiverse theories are testable in principle, but whether they're testable in practice with our current or foreseeable technology. That's a different question entirely. Many scientific ideas remained untestable for decades or centuries before technology caught up. Continental drift was proposed in 1912 but not confirmed until the 1960s. Gravitational waves were predicted in 1916 but not detected until 2015. Patience sometimes pays off. The debate ultimately reveals deep divisions about science's nature and limits. Should we only pursue theories that promise definitive experimental tests within our lifetimes? Or should we follow theoretical consistency wherever it leads, even into realms we can't directly probe? There's no obvious right answer. Both approaches have produced crucial insights throughout history. The multiverse controversy won't resolve quickly because it touches fundamental questions about how we decide what counts as legitimate science. But one thing's certain. Whether the multiverse exists or not, wrestling with the question pushes physics and cosmology into new territory, forcing us to confront the boundaries of knowledge itself. Beyond the philosophical debates and theoretical frameworks lies something more immediate. The technology we're building right now might be forcing our hand on these questions sooner than anyone expected. Google's Willow quantum chip solved the specific benchmark problem in under 5 minutes. The same calculation would take the world's fastest classical supercomputer 10 septillion years. That's longer than the age of a universe by a factor you can't easily comprehend. The number has 25 digits. Hartmut Neven, who founded Google's quantum AI team, made a striking claim about what this means. He suggested that chip's performance supports quantum computation occurring across many parallel universes. The statement ignited immediate controversy, which is exactly what happens when cutting-edge technology collides with fundamental physics. Here's the context you need. Quantum computers exploit superposition, where particles exist in multiple states simultaneously until measured. A quantum bit, or qubit, can be both 0 and 1 at the same time. String together enough qubits and you get computational power that scales exponentially, not linearly like classical bits. But where does that computational power come from? David Deutsch asked this question back in the 1980s. He pioneered quantum computing theory while simultaneously advocating for the many worlds interpretation. His answer was straightforward. The calculations are being performed across parallel universes, each handling different parts of the problem simultaneously. Consider Shor's algorithm, which can factor large numbers exponentially faster than any known classical algorithm. When a quantum computer runs this algorithm, it's testing many possible factors at once through superposition. Deutsch argued this massive parallelism only makes sense if those calculations are actually happening somewhere. Not in abstract mathematical space, but in physically real parallel branches of reality. The mainstream physics community doesn't universally accept this interpretation. Many physicists argue that quantum mechanics works perfectly well without invoking parallel universes. The math doesn't require a multiverse. It just requires taking the wave function seriously as a complete description of reality. Yet something bothers people about rejecting the many worlds view. Quantum mechanics describes particles as existing in superposition. We measure them and observe definite outcomes. The Copenhagen interpretation says measurement causes collapse, where superposition ends and one outcome becomes real. But what exactly constitutes a measurement? Where's the boundary between quantum and classical behavior? These questions have troubled physicists for nearly a century. The many worlds interpretation eliminates the measurement problem entirely. There's no collapse. Every possible outcome happens. You just find yourself in one branch experiencing one result while other versions of you experience different results in other branches. The wave function never collapses because it doesn't need to. Reality branches instead. Quantum decoherence makes this picture more rigorous. When a quantum system interacts with its environment, different possible states become entangled with different environmental states. These branches become effectively isolated from each other, unable to interfere. You experience definite outcomes not because other possibilities disappear, but because you're now correlated with one specific branch of a massively entangled system. Decoherence theory developed throughout the 1970s and 80s, giving the many worlds interpretation new mathematical teeth. It explains why we don't perceive superpositions in everyday life without requiring mysterious collapse mechanisms. Google's Willow chip brings this from pure theory into engineering reality. The device maintained quantum coherence long enough to perform calculations that classical physics can't explain efficiently. Nevin's claim that this demonstrates parallel computation across universes is provocative, but it's not scientifically settled. Critics point out that you don't need parallel universes to explain quantum computing. The standard quantum mechanical formalism works fine. Superposition and entanglement are features of the math, not necessarily proof of physically real parallel worlds. Alternative interpretations like pilot wave theory or quantum Bayesianism offer different explanations without multiplying universes. But here's what makes the quantum computing connection interesting. It's not just philosophy anymore. We're building machines that leverage whatever quantum mechanics actually is. Whether that's parallel universes or something else, the technology works. And as quantum computers become more powerful, the question of what they're actually doing becomes harder to ignore. Deutsch went further than most. He didn't just say quantum computers suggest parallel universes. He argued they provide the strongest evidence we have that the multiverse is real. Each successful quantum computation, in his view, demonstrates interference between parallel branches of reality. The fact that quantum algorithms work proves those branches exist. This remains deeply controversial. Most quantum computing researchers focus on applications rather than interpretations. They care whether the computer factors large numbers or simulates molecular structures, not whether it's accessing parallel universes to do so. Yet the interpretational questions won't disappear. As quantum computers tackle increasingly complex problems, as they demonstrate capabilities that strain classical explanations, the pressure to understand what's fundamentally happening intensifies. Think about what it means if Deutsch is right. Every quantum event in the universe constantly spawns new branches. Every particle interaction, every photon absorption, every electron transition creates new worlds. The branching happens continuously, everywhere, at microscopic scales. The number of parallel universes isn't just large. It's increasing exponentially with every passing moment. You might wonder whether this violates conservation of energy. Doesn't creating infinite universes require infinite energy? The many worlds interpretation handles this through quantum mechanics linearity. The total wave function evolves deterministically. No new energy appears. What looks like branching from inside one branch is just the smooth evolution of one universal wave function that describes all branches together. This raises profound questions about probability. Why do quantum measurements show statistical patterns? If all outcomes happen, why do some seem more likely than others? The many worlds interpretation addresses this through the Born rule, which connects the wave function's amplitude to observed frequencies. But deriving the Born rule from many worlds assumptions remains technically challenging and philosophically contentious. Some physicists argue that many worlds doesn't actually solve the measurement problem, just relocates it. Instead of explaining why we see one outcome, it must explain why we perceive ourselves as existing in one branch when we supposedly exist in all branches. The subjective experience of definite outcomes still needs accounting for. Others find this criticism misses the point. Decoherence explains why branches don't interfere, which is sufficient to explain our observations. You don't perceive multiple outcomes because your brain state is correlated with one environmental state, and decoherence prevents you from accessing information about other branches. The quantum computing angle adds urgency because it's no longer purely theoretical. Companies are investing billions in quantum technology. Governments are funding quantum research programs. The machines are getting better rapidly. Within decades, quantum computers might tackle problems completely beyond classical reach. When that happens, will the many worlds interpretation shift from philosophical curiosity to technological necessity? Or will alternative explanations prove more fruitful for understanding and improving quantum devices? Nevin's statement about Willow generated headlines precisely because it bridges this gap. A working quantum computer from a major technology company, described by its creator as evidence for parallel universes. That's not a thought experiment. It's engineering meeting metaphysics in real time. The scientific response was mixed. Some physicists welcomed the attention to foundational questions. Others worried about overstating conclusions, especially to general audiences. The calculation Willow performed, called random circuit sampling, is specifically designed to be hard for classical computers but easy for quantum ones. It's a benchmark, not a practical application. Using it to make claims about the nature of reality stretches the evidence. Yet benchmarks matter. They demonstrate capability. They push boundaries. And they force physicists to confront what their theories actually predict in concrete situations. Quantum computing might ultimately prove agnostic about interpretations. Perhaps any interpretation that reproduces quantum mechanics predictions will work equally well for building better computers. Or perhaps specific interpretational stances will guide research in more productive directions, revealing new algorithms or error correction methods. What's certain is that quantum technology is making multiverse questions more tangible. We're not just discussing whether parallel universes might exist. We're asking whether the devices on our lab benches are interacting with them. That's a different kind of conversation entirely. The connection between quantum computing and the many worlds interpretation reveals something crucial about how science progresses. Sometimes abstract theoretical debates become relevant in unexpected ways. Sometimes technology forces us to take philosophical positions seriously because they might affect practical outcomes. Whether Deutsch is right that quantum computers prove the multiverse exists remains open. But the question is no longer purely academic. It's entangled with the future of computation itself, and therefore with technology's trajectory over the coming century. Beyond quantum mechanics lies an entirely different path to the multiverse, one emerging from cosmology itself rather than the behavior of particles. This route starts not with measurements in laboratories but with observations of the universe's largest structures and deepest history. In 1979, physicist Alan Guth was trying to solve a specific technical problem in Big Bang theory. The universe appeared too uniform. Regions of space separated by distances so vast that light couldn't have traveled between them since the Big Bang somehow had nearly identical temperatures. How could causally disconnected regions coordinate their properties? Guth's answer was inflation. A brief period of exponentially rapid expansion in the universe's first fraction of a second, stretching space faster than light could cross it. This solved multiple problems simultaneously. It explained the uniformity, the flatness of space, and the absence of certain exotic particles predicted by theory but never observed. The inflationary picture seemed almost too elegant. Within about 10 to the negative 35 seconds after the Big Bang, the universe expanded by a factor of at least 10 to the 26th power. A region smaller than a proton inflated to cosmic scales, smoothing out irregularities and setting initial conditions that would eventually produce galaxies, stars, and planets. But inflation had a consequence Guth didn't initially anticipate. Once you start inflation, quantum mechanics makes it extremely difficult to stop everywhere simultaneously. Think of space as a field with an energy value. During inflation, this field sits in a high-energy state, driving the rapid expansion. Eventually, the field decays to a lower energy state, inflation ends, and normal cosmic evolution begins. That's what happened in our observable universe roughly 13.8 billion years ago. Here's where it gets strange. Quantum fluctuations in the inflaton field mean different regions decay at different times. Some regions end inflation and become universes like ours. Other regions continue inflating, and within those regions, quantum fluctuations create new pockets that stop inflating while surrounding space keeps going. This process never fully terminates. Eternal inflation produces a fractal structure where bubble universes constantly form within an eternally inflating background. Each bubble becomes a distinct universe with its own Big Bang, its own evolution, its own galaxies. Paul Steinhardt demonstrated this mechanism in 1983, showing how inflation could produce isolated bubble universes surrounded by inflating space. Later that year, Alexander Vilenkin proved this wasn't a special case requiring fine-tuning but a generic prediction of inflation. If the theory works at all, it almost certainly produces a multiverse. Andre Linde developed these ideas further with his chaotic inflation model in 1986. According to Linde's framework, there was no single beginning. Our universe emerged from a quantum fluctuation in some pre-existing region of spacetime. That region itself came from another fluctuation. The process extends infinitely backward and forward in time. This wasn't speculation disconnected from observation. NASA's Cosmic Background Explorer satellite detected exactly the pattern of temperature fluctuations inflation predicted in 1990. Those ripples in the cosmic microwave background, formed when our universe was 10 to the negative 30 seconds old, matched inflation's mathematical predictions precisely. The Wilkinson Microwave Anisotropy Probe confirmed these results in 2003, verifying inflation's prediction that the universe is geometrically flat to within 1 or 2%. These observations didn't prove eternal inflation or the multiverse directly, but they established that inflation itself happened, lending credibility to its unexpected consequences. The inflationary multiverse differs fundamentally from quantum many-worlds. These aren't different branches of possibility but physically separated regions of space. Each bubble universe is a real place, potentially with matter, energy, and physical processes, just causally disconnected from ours by the inflating space between us. Distance here means something absolute. Light from other bubble universes can never reach us because the space separating us expands faster than light travels. There's no way to send signals, no method of communication, no possibility of interaction. They're as inaccessible as regions beyond our cosmic horizon, but for a different reason. What makes this scenario particularly provocative is that different bubble universes might have different physical laws. During inflation, various fields settle into different configurations, potentially changing fundamental constants where even which forces operate. This connects to string theory, where Leonard Susskind identified what he called the landscape. String theory doesn't predict a unique set of physical laws but allows for something like 10 to the 272,000 different possible configurations. Each configuration corresponds to a different way the theory's extra dimensions could be compactified, producing different physics. Susskind proposed that eternal inflation populates this landscape. Each bubble universe randomly selects one configuration from the vast array of possibilities. Some universes have strong gravity and weak electromagnetism. Others might have different numbers of particle types or altered constants determining nuclear forces. In this populated landscape, our universe becomes one random sample from an incomprehensibly large ensemble. The specific laws we observe aren't unique or inevitable but merely the configuration that happened to arise in our particular bubble. This framework addresses what's called the fine-tuning problem. Physical constants in our universe appear calibrated with extraordinary precision to allow complex structures and life. The cosmological constant, for instance, has a value around 3 times 10 to the negative 122 in certain units. If it were even slightly larger, galaxies couldn't form. Slightly smaller, and the universe would have collapsed before stars ignited. Traditional physics struggle to explain this precision. Why should a constant take exactly the value needed for life when theory suggests it could be vastly different? Some saw this as evidence for design. Others considered it an unsolved mystery requiring deeper physics. The multiverse offers a statistical explanation. If countless universes exist with randomly varying constants, some will inevitably have values permitting complexity and observers. We find ourselves in such a universe not because it's special but because observers can only exist where conditions allow observation. This reasoning invokes the anthropic principle. We necessarily observe a universe compatible with our existence, regardless of how improbable that universe might be in isolation. With infinite trials across the multiverse, even extremely unlikely configurations become guaranteed somewhere. Critics find this logic troubling. It seems to give up on explaining why constants have specific values, replacing derivation with selection. Rather than finding fundamental principles that require the cosmological constant to be 3 times 10 to the negative 122, we simply note that we couldn't exist if it were different. Defenders counter that this might be how nature actually works. If the landscape exists and inflation populates it, anthropic reasoning isn't giving up on explanation but recognizing the explanation's true form. Not all questions have answers in terms of unique mathematical necessity. The debate reveals tension between different visions of physics. One vision seeks unique, derivable laws following from mathematical elegance or symmetry principles. Another accepts that some aspects of reality might be environmental accidents, products of cosmic history rather than logical inevitability. Eternal inflation also raises bizarre questions about probability and measure. If infinitely many bubble universes exist, how do you calculate the likelihood of observing particular properties? Standard probability breaks down with infinite sets because you can't count what fraction has specific features. This measure problem has occupied cosmologists for decades. Different mathematical approaches to defining probability and eternal inflation give different predictions. Some measures favor universes where observers are rare. Others predict we should see different physical constants than we actually observe. No consensus solution exists yet. The measure problem represents a fundamental challenge to making eternal inflation fully predictive rather than merely explanatory after the fact. There's also the question of what inflation actually is. The inflaton field driving expansion remains hypothetical. We've never detected it directly or identified what particle or field it corresponds to in fundamental physics. Inflation works mathematically and explains observations, but its physical basis remains uncertain. Some physicists explore alternatives to inflation that might avoid multiverse implications. Cyclic cosmology, for example, suggests the universe undergoes repeated cycles of expansion and contraction without requiring eternal inflation. These models remain speculative and face their own challenges. Yet inflation's observational support is substantial. The cosmic microwave background's detailed properties match its predictions remarkably well. Alternative explanations exist, but none combine simplicity, predictive power, and observational agreement quite like inflation. If inflation happened and Vilenkin is right that eternal inflation is generic, the multiverse follows almost inevitably. You can accept inflation successes while hoping eternal inflation is somehow wrong, but that requires finding special conditions that stop inflation globally, something most models don't naturally provide. The inflationary multiverse thus occupies an unusual position. It emerges from well-tested physics, is supported by observations, and follows logically from established theory. Yet it predicts unobservable entities and relies on reasoning that makes some physicists deeply uncomfortable. This discomfort intensifies when considering the landscape. String theory itself remains unconfirmed experimentally. Combining it with eternal inflation to populate the landscape stacks speculation on speculation, even if each component has independent motivation. But here's what makes the situation genuinely difficult. If the multiverse exists, we should expect to find ourselves in a typical universe among those supporting observers. Our universe's properties should be common in the habitable subset, not unusual. Some features match this expectation. Others don't, creating ongoing debates about what the multiverse actually predicts. String theory offers yet another multiverse variant through brane cosmology. Imagine our three-dimensional universe as a membrane floating in higher dimensional space. Other universes could be nearby branes, separated from us in dimensions we can't perceive, potentially close enough in the extra dimensions to occasionally interact. The brane scenario emerged from string theory during the late 1990s and early 2000s, driven by discoveries about higher dimensional objects called branes. String theory requires extra spatial dimensions beyond the familiar three. These extra dimensions must be compactified, curled up so tightly we don't notice them. But what if some of those dimensions aren't microscopic? What if they're large or even infinite, and we're simply confined to a three-dimensional slice? Picture a sheet of paper floating in a room. Everything you experience, every particle you're made of, every force except gravity, is stuck to that sheet. You can move anywhere on the paper's surface but can't step off into the surrounding space. That's the brane universe concept. Our cosmos would be a three-dimensional membrane embedded in higher dimensional space called the bulk. Other branes could exist in that same bulk, potentially very close to ours in the extra dimensions. Two sheets of paper can be millimeters apart while objects on each sheet never interact directly. Similarly, another universe could be nearby in a dimension we can't access or perceive. This proximity creates possibilities absent from other multiverse types. Branes might occasionally collide. Some cosmological models propose that the Big Bang itself resulted from a collision between branes in higher dimensional space. The cyclic model of Paul Steinhardt and Neil Turok suggests branes repeatedly collide, producing cycles of cosmic death and rebirth that avoid the singularity problems of traditional Big Bang cosmology. Brane collisions could leave observable signatures. If another brane crashed into ours billions of years ago, we might detect the impact's remnants in cosmic microwave background patterns or large-scale structure distribution. Researchers have searched for such signals without definitive results, but the possibility remains. Gravity behaves differently in brain scenarios. While other forces are confined to our brain, gravity propagates through the bulk, potentially explaining why it's so much weaker than electromagnetism or the nuclear forces. Its strength gets diluted across extra dimensions while other forces remain concentrated on our brain. This framework addresses hierarchy problems in physics, particularly why gravity is roughly 40 orders of magnitude weaker than other fundamental forces. If gravity spreads through large extra dimensions while other forces don't, the apparent weakness follows naturally without requiring extreme fine-tuning. Experimental tests have been proposed. If large extra dimensions exist, gravity's behavior should deviate from predictions at small distances. Precision measurements of gravitational force at submillimeter scales could reveal these deviations. So far, experiments confirm standard predictions, constraining but not eliminating the possibility. The brain multiverse differs fundamentally from eternal inflation's bubbles. Brain universes could be physically close in extra dimensions despite being completely separate in ordinary space. They might influence each other through gravity or rare collisions. This creates a more interactive multiverse than isolated bubble universes. Yet brain cosmology faces significant challenges. String theory itself remains unconfirmed. We have no direct evidence for extra dimensions, brains, or the specific mechanisms proposed. The models are mathematically rich and address real problems, but empirical support is limited. The cyclic model, while elegant, makes predictions about primordial gravitational waves that upcoming observations might test. If cosmic inflation occurred, it should have produced a specific gravitational wave background. If cyclic collisions happened instead, the signature would differ. These observations could distinguish between frameworks. Meanwhile, quantum mechanics offers its own multiverse through the many-worlds interpretation. Unlike cosmological multiverses arising from inflation or string theory, this multiverse emerges directly from quantum theory's mathematical structure without adding new physics. Hugh Everett proposed this interpretation in 1957, arguing that quantum mechanics describes a universe constantly branching into parallel versions. Every quantum event splits reality into multiple branches, each representing a different outcome. The electron goes through the left slit in one branch, the right slit in another. Both outcomes are real, occurring in different branches of the universal wave function. This interpretation eliminates the measurement problem that plagued quantum mechanics. In the Copenhagen interpretation, measurement causes wave function collapse, but what counts as measurement? When exactly does collapse occur? These questions never had satisfying answers. Everett's approach makes them irrelevant. There is no collapse. The wave function evolves deterministically, and observers simply become entangled with the systems they measure. When you measure an electron spin, you don't collapse its wave function. Instead, you enter a superposition. In one branch, you observe spin up. In another, you observe spin down. Both versions of you exist in different branches, each experiencing a definite outcome. Quantum decoherence, developed decades after Everett's work, provides the mechanism explaining why we experience definite outcomes. When quantum systems interact with their environment, different branches become effectively isolated. Information spreads into the environment so rapidly that interference between branches becomes practically impossible. This explains why we never experience quantum superpositions directly, why cats appear either alive or dead rather than both. The many-worlds interpretation makes identical predictions to other quantum interpretations for all measurable quantities. It's empirically equivalent to Copenhagen or other formulations. The difference lies in ontology, in what these interpretations claim about reality's fundamental nature. Critics argue many worlds is extravagant, multiplying entities beyond necessity. Why accept countless unobservable branches when simpler interpretations exist? Proponents counter that many worlds is actually more economical. It takes quantum mechanics equations seriously without adding collapse mechanisms or special measurement rules. The multiverse emerges from the math rather than being imposed. David Deutsch connected many worlds to quantum computing in the 1980s. Quantum computers can solve certain problems exponentially faster than classical computers by exploiting superposition and interference. Deutsch argued this computational power makes sense if quantum computers utilize resources from parallel branches. A quantum computer with 300 qubits accesses 2 to the power of 300 computational states simultaneously, more than there are atoms in the observable universe. Where does that computational space exist if not across parallel worlds? Recent quantum computing achievements have renewed this discussion. Google's Willow chip and other quantum processors perform calculations that would take classical supercomputers thousands of years. Hartmut Neven suggested this supports many worlds, though critics argue other interpretations explain these results equally well. The debate continues because quantum interpretations remain empirically indistinguishable. They make identical predictions for all experiments we can perform. Choosing between them involves philosophical preferences about simplicity, realism, and what constitutes satisfactory explanation rather than pure empirical testing. Some physicists dismiss interpretation debates as meaningless philosophy. Shut up and calculate became a common attitude. Just use quantum mechanics to make predictions without worrying about what it means. But interpretation questions have practical implications for understanding quantum foundations, developing new technologies, and unifying quantum mechanics with gravity. The many worlds interpretation also raises profound questions about probability and personal identity. If all outcomes occur, what does it mean to say one outcome is more likely than another? In standard quantum mechanics, probabilities determine measurement results. In many worlds, every result happens in some branch. How do we recover probabilistic predictions? The Born rule, giving outcome probabilities from wave function amplitudes, must be derived rather than assumed in many worlds. Deutsch and others have attempted such derivations using decision theory, arguing that rational observers should behave as if outcomes have Born rule probabilities even though all outcomes occur. These derivations remain controversial. Personal identity becomes puzzling. If you split into multiple copies at each measurement, which one is really you? All of them? The question might be meaningless, like asking which water molecule in a river is the river itself. Perhaps personal identity is approximate, a useful fiction that breaks down when examining quantum branching closely. Max Tegmark organized these diverse multiverse types into a 4-level hierarchy. Level 1 covers distant regions beyond our cosmic horizon, separated only by space. Level 2 includes eternal inflation's bubble universes with different physical constants. Level 3 is the many worlds interpretation's quantum branches. Level 4, the most speculative, proposes that all mathematically consistent structures exist as physical realities. This ultimate multiverse suggests that mathematical existence equals physical existence. Every possible mathematical structure, every consistent set of equations, corresponds to an actual universe. Our universe is one mathematical structure among infinitely many. Physics becomes a branch of mathematics, and the question of why our universe exists dissolves into the tautology that all possible universes exist. Critics find level 4 absurd, untestable speculation masquerading as theory. Proponents argue it's the natural endpoint of taking mathematical descriptions of reality seriously. If our universe is fundamentally mathematical, why should only one mathematical structure be real? Brian Greene expanded Tegmark's taxonomy to 9 types, including simulated and holographic multiverses. The simulation hypothesis suggests our reality might be a computer simulation run by advanced beings in a higher reality. If civilizations eventually create detailed simulations, simulated realities could vastly outnumber base reality, making it statistically likely we're simulated. The holographic principle, emerging from black hole thermodynamics and string theory, suggests our three-dimensional universe might be encoded on a two-dimensional boundary. This creates a kind of multiverse where different holographic descriptions represent the same physics, though this differs from other multiverse types. These classifications reveal the multiverse's conceptual diversity. Different theories predict different types of parallel universes through entirely different mechanisms. They're not variations on a single theme but distinct proposals emerging from separate areas of physics. What unites them is a willingness to accept that reality extends beyond direct observation. Science has repeatedly discovered that the universe is larger and stranger than it appears. Earth isn't the center. The Milky Way isn't the only galaxy. The observable universe isn't everything. Perhaps other universes exist beyond our cosmic horizon or quantum measurements or extra dimensions. Yet testability remains the central controversy. How do you verify something that exists beyond all possible observation? Traditional science demands that theories make predictions testable through experiment or observation. Multiverse theories appear to violate this principle fundamentally. If other universes are causally disconnected from ours, no measurement we perform can detect them. No experiment can confirm or refute their existence. This troubles many physicists deeply. George Ellis argues that multiverse theories abandon scientific methodology. Invoking infinite unobservable universes to explain our universe's properties resembles invoking an unseen creator. Both require faith in entities beyond empirical verification. The multiverse may wear scientific language, but it functions like metaphysics dressed in equations. Ellis points out that these other universes are theorized to exist so far beyond any observational horizon that evidence will never arrive. If a theory makes no testable predictions, is it science? Defenders counter that indirect testing remains possible. Many accepted physics concepts involve unobservable entities. Quarks couldn't be directly observed initially. We inferred their existence from particle collision patterns. Regions beyond our cosmic horizon are definitionally unobservable, yet we accept they exist based on extrapolating known physics. The multiverse might fall into this category. Furthermore, some multiverse predictions are testable. If eternal inflation produces bubble universes, collisions between bubbles might leave detectable imprints in the cosmic microwave background. Researchers have searched for such signatures. None have been found conclusively, but the search continues. String theory's landscape might predict statistical patterns in particle physics or cosmology. These predictions, while difficult to test, aren't impossible. The debate over Occam's razor cuts both ways. Critics argue that postulating infinite universes violates simplicity. Why multiply entities beyond necessity? One universe requires less assumption than infinitely many. But proponents flip this reasoning. Which is simpler, fine-tuning a single universe's constants to improbable precision, or accepting that all possible constants are realized somewhere? The multiverse eliminates the need for special explanation of our universe's properties. It trades one mystery for a different kind of simplicity. Leonard Susskind faced this dilemma directly with string theory. String theory promised to be the ultimate theory of everything, uniquely determining all physical laws. Instead, It produced a landscape of 10 to the power of 272,000 possible vacuum states, each corresponding to different physics. This seemed like failure. String theory couldn't predict our universe uniquely. Suskind's solution was radical: embrace the landscape. Combine it with eternal inflation. Every vacuum state is realized in some bubble universe. Our universe's properties aren't uniquely predicted because they're not unique. We observe our particular physics because we exist in one of the rare bubbles where observers can exist. This rescued string theory from its predictive problem while introducing the populated landscape concept. The anthropic principle becomes crucial here. Our universe's constants appear fine-tuned for life. The cosmological constant, for instance, has a value around 3 × 10⁻122. If it were slightly larger, galaxies couldn't form. Slightly smaller, and the universe would have recollapsed. This precision seems to demand explanation. Traditional physics seeks a fundamental reason why constants have their values. The anthropic approach says we observe life-permitting values because only such universes contain observers. In a multiverse with varying constants, observing life-compatible physics is inevitable. We're guaranteed to find ourselves in a habitable universe because we couldn't exist elsewhere. This reasoning disturbs many physicists. It feels like giving up on finding deeper explanations. Rather than deriving constants from fundamental principles, we're saying they're random environmental variables. Imagine asking why Earth's temperature supports life. One answer: Earth formed at the right distance from the Sun. Deeper answer: planetary formation physics and stellar evolution determine habitable zones. Anthropic answer: countless planets exist, and we necessarily find ourselves on one that's habitable. The anthropic approach works but feels unsatisfying. It trades explanation for selection effect. Yet our universe's fine-tuning is extreme. The cosmological constant problem is particularly severe. Quantum field theory predicts a vacuum energy 120 orders of magnitude larger than observed. This represents the worst prediction in physics history. Why is the actual value so incredibly small yet non-zero? If a multiverse exists with varying constants, this mystery dissolves. Most universes have enormous cosmological constants and no structure. We observe a tiny value because only such universes support galaxies, stars, and observers. The anthropic explanation works perfectly here, even if it's philosophically uncomfortable. The simulation hypothesis adds another layer. If advanced civilizations can create detailed simulated realities, and if they run many such simulations, then simulated realities vastly outnumber base reality. Statistically, we're more likely to inhabit a simulation than the original universe. This creates a strange kind of multiverse where different simulations represent different realities, all running on computational substrate in some higher level. The hypothesis is unfalsifiable currently, but it raises genuine questions about reality's nature. Quantum computing has reignited multiverse debates recently. Google's Willow chip solved the benchmark problem in 5 minutes that would take classical supercomputers 10 septillion years. Hartmut Neven suggested this supports many worlds interpretation, implying the chip performs calculations across parallel universes. David Deutsch made similar arguments decades earlier. Quantum computers' power only makes sense if they access computational resources from the multiverse. Critics argue this interpretation isn't necessary. Quantum mechanics works without ontological commitment to parallel worlds. The mathematics allows multiple interpretations. Many worlds is one, but quantum computing doesn't prove it. This highlights a fundamental issue. Physics uses mathematics to describe reality, but mathematics allows multiple interpretations. The equations work regardless of whether parallel universes physically exist. Many worlds, Copenhagen interpretation, pilot wave theory, all make identical predictions. They differ philosophically about what's real, not empirically about what's measured. Quantum computing demonstrates quantum mechanics' power but doesn't settle interpretational debates. Where does this leave us? The multiverse landscape is diverse and fragmented. Different theories predict different types of parallel universes through unrelated mechanisms. Eternal inflation produces bubble universes. Quantum mechanics produces branching worlds. String theory produces landscape variations. These aren't variations on one theme but distinct proposals from separate physics areas. What unites them is accepting that reality extends beyond direct observation. This represents a profound shift in scientific thinking. For centuries, science progressed by observing, measuring, testing. The multiverse challenges this model. It asks us to accept entities that might be permanently beyond observation based on theoretical consistency and indirect reasoning. Some physicists embrace this. Others see it as abandoning science's empirical foundation. The question isn't settled. Perhaps future observations will provide evidence. Perhaps improved theories will eliminate the need for multiverses. Perhaps we'll develop new verification methods. Or perhaps we'll accept that some questions exceed empirical investigation's limits while remaining scientifically meaningful. The multiverse forces confrontation with deep questions about science's nature and limits. What makes a theory scientific if not testability? Can inference and consistency substitute for direct observation? Where does physics end and metaphysics begin? These aren't just abstract philosophical questions. They determine how we practice science, what theories we pursue, what explanations we accept. Meanwhile, the universe we observe remains stubbornly singular. We see one set of physical laws, one cosmic history, one reality. Whether countless others exist beyond our reach or whether our universe stands alone remains unknown. The equations suggest possibilities. The observations remain silent. And physics continues pushing against the boundaries of what can be known, discovering repeatedly that reality exceeds our expectations and perhaps ultimately our ability to fully comprehend. The multiverse stands as the latest chapter in this ongoing story, where human curiosity confronts the cosmos and asks whether what we see is all there is. The multiverse question has pushed physics into genuinely uncomfortable territory. We've built theories that work spectacularly well at describing reality, and those same theories keep pointing toward things we can't observe. That's not how science usually operates, but it might be how the universe actually is. Consider where we stand. Quantum mechanics, tested to extraordinary precision over a century, seems to describe branching realities whether we like it or not. Cosmic inflation, confirmed by satellite observations of the early universe, naturally produces eternal inflation and bubble universes as a generic consequence. String theory, despite remaining unproven, generates a landscape of possibilities that eternal inflation could populate. None of these theories were designed to produce multiverses. The multiverses emerged as unavoidable implications. This creates genuine tension. Science traditionally demands testability. Propose a hypothesis, design experiments, check if nature agrees. The multiverse appears to violate this principle fundamentally. Other universes exist beyond any horizon we could ever reach. No light from them will arrive. No measurement can detect them. They're causally disconnected by definition. Yet physics already accepts many unobservable things. Quarks can't be isolated and observed directly. Black hole interiors lie permanently beyond observation. Regions beyond our cosmic horizon will never be visible. We accept these based on theoretical consistency and indirect evidence. The multiverse might simply extend this pattern further. The real question isn't whether the multiverse is testable in the traditional sense. It's whether the theories predicting multiverses are testable. Quantum mechanics is extraordinarily well tested. Inflation has passed multiple observational checks. String theory remains speculative but addresses real problems. If these frameworks prove correct through testing their accessible predictions, do we reject their inaccessible implications? Some physicists say yes, absolutely. Others argue that would be arbitrary, cherry-picking which parts of successful theories to accept. If quantum mechanics works and its math describes branching universes, rejecting those branches because we can't visit them seems inconsistent. If inflation happened and eternal inflation follows generically, denying the multiverse requires special pleading. The anthropic principle adds another dimension. Our universe's constants appear fine-tuned with absurd precision. The cosmological constant problem alone represents a discrepancy of 120 orders of magnitude between theory and observation. Traditional physics seeks fundamental reasons for specific values. The multiverse offers statistical explanation. With infinite universes exploring all possible constants, some inevitably permit structure and observers. We exist in such a universe because we couldn't exist anywhere else. This reasoning works but feels unsatisfying. It trades derivation for selection. Rather than explaining why constants have specific values, it says they're environmental variables varying across the multiverse. Many physicists find this intellectually disappointing, abandoning the goal of understanding why our universe is the way it is. But maybe that's the answer. Maybe some features of reality are environmental accidents rather than logical necessities. Biology accepted this long ago. Earth's properties aren't uniquely determined by fundamental principles. They're products of history, contingency, chance. Perhaps physics must accept similar conclusions about the universe itself. The measure problem complicates eternal inflation's predictions. With infinitely many bubble universes, calculating probabilities becomes mathematically subtle. Different approaches to defining probability in infinite sets give different answers. This technical challenge prevents eternal inflation from making sharp predictions about what typical observers should see. The framework explains our universe's existence but struggles to predict its detailed properties. Quantum many-worlds faces analogous issues. If all outcomes occur, deriving the Born rule for quantum probabilities requires additional assumptions. Why should observers experience outcomes with frequencies matching wave function amplitudes if every outcome happens? Various derivations exist, using decision theory or information theory, but none are universally accepted. The interpretation makes sense conceptually, but deriving its quantitative predictions from first principles remains challenging. String theory's landscape is even more speculative. String theory itself lacks experimental confirmation. Combining it with eternal inflation to populate the landscape stacks hypothesis on hypothesis. The framework addresses real problems, fine-tuning, and string theory's lack of unique predictions, but it does so by embracing vast unobservable structures. These challenges are real. The multiverse might be wrong. Better theories might emerge that explain fine-tuning through fundamental principles rather than anthropic selection. New observations might rule out inflation or find alternatives that avoid eternal inflation. Quantum mechanics might receive a reformulation that eliminates many worlds. String theory could fail, making its landscape irrelevant. But right now, today, the multiverse represents where our best theories point. Not because physicists want infinite unobservable universes, but because the math keeps suggesting them. Rejecting the multiverse means either rejecting successful theories or claiming we understand exactly where those theories stop applying, which seems presumptuous. The question ultimately comes down to how we practice science at the frontiers of knowledge. Do we follow theoretical consistency wherever it leads, even beyond observation? Or do we impose strict empirical standards, rejecting anything untestable regardless of theoretical motivation? Both approaches have merit. Both have produced important insights historically. The multiverse debate reveals we haven't resolved this tension. Technology might force the issue. Quantum computers are improving rapidly. If they continue demonstrating capabilities that strain classical explanation, the many worlds interpretation might shift from philosophical curiosity to practical framework. Not because it's proven, but because it guides thinking productively about what quantum systems actually do. Cosmological observations could detect bubble collisions or other multiverse signatures. Unlikely, but possible. One clear detection would transform speculation into established fact overnight. The absence of such signatures doesn't disprove the multiverse, just limits what we can say about it. Meanwhile, physics continues developing. New theories emerge, existing ones get refined, observations accumulate. The multiverse question won't resolve quickly because it touches fundamental issues about science's nature and limits. But engaging with it seriously, even skeptically, pushes physics forward. It forces clarification of assumptions, development of new mathematical tools, and confrontation with deep questions about reality. Perhaps the multiverse exists. Perhaps it's an artifact of taking provisional theories too literally. Perhaps the question itself is malformed, resting on assumptions we'll eventually recognize as naive. We don't know yet. But the journey of trying to find out, of pushing against the boundaries of the knowable, represents science operating exactly as it should. The cosmos has surprised us before. Earth isn't the center. The sun isn't unique. The Milky Way isn't the only galaxy. The universe is vastly older and larger than once imagined. Each discovery revealed that reality exceeded previous conception. The multiverse might be the next step in this progression, or it might be where we finally hit the limits of what physics can meaningfully discuss. Either way, the question matters. Not just for understanding the universe, but for understanding what it means to understand. Science isn't just accumulating facts. It's developing frameworks for making sense of reality, pushing those frameworks to their limits, and discovering whether those limits lie in nature or in us. The multiverse stands at that edge right now. A place where mathematics points beyond observation, where theoretical consistency conflicts with empirical verification, where the tools that brought us this far might not carry us further. Whether other universes exist or not, wrestling with the question reveals something true about our relationship with the cosmos. We're trying to comprehend something vastly larger than ourselves using minds shaped by evolution for entirely different purposes. That we can ask these questions at all, that we can build theories suggesting answers, remains remarkable regardless of whether those answers are correct. So the multiverse remains open. A genuine scientific question without a settled answer, representing both physics at its most ambitious and its most uncertain. The equations work. The observations are limited. The implications are staggering. And somewhere in that space between what we can calculate and what we can confirm lies a truth about reality that we're still learning to ask properly.